Will we ever leave our solar system? At this very moment, a machine built before many of you were born is racing through absolute darkness, 25 billion miles from home. It's the farthest any human creation has ever ventured. Yet here's the humbling truth. It would take this probe 3,000 years to reach our nearest neighboring star. We're about to journey beyond everything familiar. We'll explore spacecraft that ride nuclear shockwaves, encounter theoretical civilizations harvesting entire stars, and confront the possibility that the universe itself has an expiration date. What we're about to discover will fundamentally change how you understand our place in the cosmos. Picture yourself standing at the ocean's edge, waves stretching toward every horizon. You might think our solar system ends at Pluto, but you'd be mistaken. Far beyond that distant ice world lies a region called the heliopause, where the sun's influence finally surrenders to the void. This invisible boundary sits 11 billion miles from Earth. Sunlight itself takes 16 hours just to reach it. If you could drive there at highway speed without stopping, the journey would consume 12 million years. Our solar system resembles a massive soap bubble floating in space. The sun inflates this bubble with solar wind, a relentless stream of charged particles racing outward at over 1 million miles per hour. For billions of miles, this stellar breath pushes against emptiness, creating a protective cocoon around everything we've ever known. But eventually, even our star's mighty exhalation weakens. At the heliopause, our cosmic bubble collides with the fierce currents of interstellar space. Here, particles from distant stars crash into our neighborhood like waves against a seawall. Temperatures plummet toward absolute zero. The very fabric of space transforms. You've crossed beyond the reach of the only star humanity has ever called home. Voyager 1 pierced this boundary in 2012, becoming the first human-made object to enter true interstellar space. Its radio whispers now take over 21 hours to reach Earth. The probe transmits signals from a realm so foreign that our brightest scientists are still deciphering their meaning. But here's what should make you pause. This edge, this frontier that required 35 years to reach with our fastest spacecraft, represents less than 1/100,000th of the distance to our nearest stellar neighbor. Imagine taking a single step on a path that circles Earth 2.5 million times. That's how far we've come compared to how far we need to go. The heliopause isn't merely a border, it's a warning. Beyond this threshold, the rules change completely. Our sun's gentle warmth becomes irrelevant. The magnetic shields protecting us from lethal radiation vanish. Even time behaves differently when you're moving between stars at impossible velocities. Standing at this cosmic shore, you realize that escaping our solar system isn't simply about engineering faster rockets or superior technology. It's about becoming something entirely new, a species capable of enduring the vast, frozen darkness between worlds. But our first ambassadors to this alien realm have already begun sending back the secrets we'll need. 2 golden records spin through the void, carrying Earth sounds toward civilizations we may never encounter. Launched in 1977, Voyager 1 and 2 were designed to explore Jupiter and Saturn, then quietly fade into obscurity. Instead, they became humanity's first interstellar ambassadors, racing toward distant stars with messages from a blue world they'll never see again. Each probe carries a golden record containing whale songs, crying babies, and music from every corner of Earth. A cosmic message in a bottle. Voyager 1 travels at 38,000 miles per hour, faster than any spacecraft in history. At this speed, you could fly from New York to Los Angeles in 4 minutes. Yet after 46 years of flight, it has barely begun its stellar journey. The probe won't approach another star for 40,000 years. These spacecraft resemble medieval ships setting sail for unknown continents. Their captains knew they might never return, but they carried the hopes of everyone left behind. Voyager's computers possess less processing power than your smartphone. Yet they continue functioning in conditions that would annihilate any earthly machine within seconds. The cold out there doesn't just freeze matter. It alters the fundamental structure of atoms. Metal becomes brittle as glass. Electronics that operated flawlessly for decades begin failing in ways engineers never anticipated. The probes are slowly dying, their nuclear hearts weakening with each passing year. But these dying messengers have already revolutionized our understanding of what lies beyond. They've detected magnetic fields twisted into impossible geometries by stellar winds. They've measured cosmic rays from galaxy-destroying explosions that occurred before Earth even existed. Most astonishing of all, they've discovered that interstellar space isn't empty. It's filled with a tenuous soup of hydrogen atoms and mysterious particles from the universe's birth. Every day, Voyager's radio signals grow fainter. By 2025, the probes will fall silent forever, their nuclear power finally exhausted. They'll become ghost ships sailing through an ocean of stars, carrying our golden records to destinations we can only imagine. Scientists estimate that in roughly 300 million years, long after humans have either evolved beyond recognition or vanished entirely, one of these records might be discovered by an alien civilization. They'll hear our music, our languages, our laughter. They'll learn that once, on a small blue planet, there lived a species audacious enough to throw bottles into the cosmic ocean. But Voyager taught us something more crucial than what exists out there. It demonstrated that we can build machines resilient enough to survive the journey between stars. The real question isn't whether we can reach other solar systems. It's whether we can survive long enough to make the attempt. And that brings us to the most terrifying discovery of all. Between here and our nearest neighbor lies a darkness so complete it makes the deepest ocean trench appear brilliantly lit. Space isn't merely empty. It's aggressively, violently empty in ways that human minds struggle to comprehend. If you scaled our solar system until Earth became the size of a marble, the nearest star would sit 1,400 miles away. That's equivalent to placing a marble in New York and expecting to strike another marble in Denver with a perfect throw. But the emptiness runs deeper than distance. In the finest vacuum chambers on Earth, scientists can remove nearly all air, leaving about 10 million particles per cubic centimeter. In interstellar space, there's less than 1 atom per cubic centimeter. You could compress all the matter between stars into a volume smaller than a grain of sand. Imagine attempting to swim across an ocean where the water is so thin you can't perceive it, so cold it would freeze your blood instantly, and so saturated with invisible radiation that it would incinerate your DNA from within. That's what spacecraft face in the void between stars. This emptiness manipulates physics itself. Without air to transmit sound, the universe becomes eternally silent. Without matter to conduct heat, temperatures hover just above absolute zero, -450 degrees Fahrenheit. At these temperatures, even helium solidifies, metal shatters like glass, electronics fail for reasons scientists are still investigating. The radiation out there makes Chernobyl resemble a health resort. Cosmic rays, particles accelerated by dying stars and black holes, collide with anything in their path at nearly light speed. A single cosmic ray carries more energy than a baseball thrown at 60 miles per hour, concentrated into a space smaller than an atom. These invisible projectiles would shred human DNA, causing cancer, brain damage, and death within months. The magnetic field that shields us on Earth disappears completely in interstellar space. Solar winds from distant stars create electromagnetic tempests that could incinerate any electronics we dispatch. Imagine using your phone during a lightning storm lasting centuries. Perhaps most unsettling, this emptiness isn't uniform. Space between stars contains hydrogen clouds, cosmic dust, and mysterious dark matter that we can detect but not understand. These clouds can stretch for hundreds of light years, creating invisible barriers that could damage or obliterate anything moving through them at high velocity. Flying through interstellar space at the speeds required to reach other stars would resemble driving through a sandstorm at 200 million miles per hour. Every dust speck becomes a bullet. Every gas cloud becomes a wall of destruction. Yet somewhere in this hostile void, we've detected something that transforms everything about how we conceive space travel. Our next destination makes this emptiness look crowded. 4.25 light years away, burns a star so dim you need a telescope just to see it. Yet it holds the key to humanity's survival. Proxima Centauri is our nearest stellar neighbor, a red dwarf star barely 1/8 the size of our Sunday. If our sun is a roaring bonfire, Proxima is a dying candle flickering in the cosmic wind. This tiny star produces so little light that its potentially habitable planet receives only 1% of the energy Earth gets. But here's what should captivate you. That planet, Proxima b, sits in the Goldilocks zone where liquid water can exist. It's just 4.25 light years away, practically next door in cosmic terms. At the speed of our fastest spacecraft, the journey would take only 73,000 years. For an immortal species, that's practically a weekend excursion. Think of Proxima Centauri as a lighthouse on a distant shore. You can see its beacon. You know exactly where it stands. But the ocean between you and safety teems with storms that could destroy any ship you build. The star itself weighs only 12% as much as our Sunday. Yet it unleashes solar flares that make our worst space weather seem gentle. These stellar tantrums release more energy in minutes than humanity has generated throughout recorded history. The flares bombard Proxima b with radiation levels that would sterilize the surface and strip away any atmosphere. If life exists there, it would need to hide deep underground or develop shielding that makes our best technology appear like paper armor. Red dwarf stars like Proxima live for trillions of years, hundreds of times longer than our sun will survive. While our solar system perishes in 5 billion years, Proxima Centauri will still burn when the universe itself grows cold and dark. It's the ultimate long-term destination for a species planning to outlive stellar death. But the journey represents humanity's greatest challenge. Moving at 10% light speed, faster than anything we've ever constructed, would still require 43 years. An entire human lifetime spent crossing the void between worlds. Babies born on the ship would age and die without ever glimpsing their destination. The energy required defies imagination. You'd need to convert matter directly into energy using Einstein's famous equation. The fuel alone would outweigh entire mountains. Even if we solve the energy problem, cosmic radiation during decades of flight would prove lethal to any human crew. Yet scientists have already detected dozens of potentially habitable planets around red dwarf stars within 50 light years of Earth. These ancient suns offer humanity something our own star cannot: time. Billions of years to evolve, explore, and spread across the galaxy before the last stars extinguish. Proxima Centauri isn't just our nearest neighbor, it's our cosmic life insurance policy. But reaching it requires us to challenge the most fundamental speed limit in the universe. And that's where Einstein's rules turn everything upside down. Nothing with mass can ever reach light speed, and that one fact might condemn humanity to perish on a single world. Einstein discovered that as you approach light speed, something impossible occurs. Your mass increases toward infinity. Pushing even a single atom to light speed would require all the energy in the universe. It's not merely difficult. It's mathematically impossible, encoded into reality's fabric like a cosmic speed limit enforced by physics itself. Light travels at 671 million miles per hour. At this velocity, you could circle Earth 7.5 times in 1 second. You could reach the moon in 1 1/3 seconds. You could traverse our entire solar system in 11 hours. Yet even at this staggering speed, reaching Proxima Centauri would consume 4.25 years. Consider light speed as the ultimate highway limit. Except the penalty for attempting to break it isn't a ticket. It's the complete annihilation of physics as we understand it. As spacecraft approach light speed, time itself begins decelerating relative to the rest of the universe. At 99% light speed, 1 year on your ship equals 7 years on Earth. This creates what scientists call the time dilation paradox. A crew traveling to Proxima Centauri at near light speed might experience only months of flight time, while everyone they left behind ages decades. They'd return to discover their friends and family deceased, their civilization transformed beyond recognition. They'd become time travelers trapped in a future they never chose. But the energy requirements render even this scenario impossible with current technology. Accelerating a spacecraft weighing as much as the space shuttle to just 10% light speed would require the energy output of the entire United States for over 100 years. Reaching 90% light speed would demand more energy than our sun produces in a century. Even if we solve the energy problem, relativistic effects transform space dust into cosmic projectiles. At near light speeds, a sand grain impacts with the force of a nuclear weapon. The thin gas between stars becomes a radiation wall that would vaporize any known material. The universe itself becomes hostile to high-speed travel. Yet Einstein's equations also revealed something extraordinary. While nothing can travel faster than light through space, space itself can expand faster than light. The universe has been doing precisely this since the Big Bang. During cosmic inflation, space regions separated faster than light could travel between them. This loophole in Einstein's laws opens a door to something resembling pure science fiction. We might not need to travel faster than light if we can convince space itself to transport us. Instead of pushing through the cosmic speed limit, we could ride spacetime's expansion itself. But harnessing this power requires technology so advanced, it might as well be magic. Our first attempt to beat Einstein employs the most violent force in the universe. Imagine riding a surfboard on a wave of nuclear explosions, each blast powerful enough to level a city. Project Orion, conceived in the 1950s, proposed the most audacious spacecraft design in human history, a ship propelled by detonating atomic bombs behind a massive steel plate. Every few seconds, another nuclear weapon would explode, thrusting the craft forward with forces that would pulverize ordinary materials. The physics actually works. Nuclear explosions release more energy per pound than any other known reaction. A single atomic bomb contains enough energy to power New York City for 2 weeks. Chain together thousands of these explosions, and you could accelerate a massive spacecraft to 5% light speed, fast enough to reach Proxima Centauri in less than a century. Think of it as the ultimate rocket, except instead of burning gasoline, you're detonating hydrogen bombs every 3 seconds and riding the shock wave. The spacecraft would require shock absorbers the size of buildings and a pusher plate constructed from materials capable of surviving repeated nuclear blasts. Engineers calculated that such a ship could weigh thousands of tons, yet still achieve speeds no chemical rocket could dream of. The original Orion design included a crew compartment protected by layers of lead shielding. Astronauts would experience brief moments of crushing acceleration, followed by weightlessness as the ship coasted between explosions. It would feel like riding inside a giant hammer being struck by an angry god's fist. But the radiation exposure would prove lethal. Each nuclear pulse would flood the spacecraft with gamma rays, neutrons, and radioactive particles. Even with heavy shielding, crew members would absorb radiation doses causing cancer, sterility, and death. The ship itself would become so radioactive that approaching it without protection would be suicide. Modern versions of pulse propulsion employ fusion instead of fission, creating cleaner explosions with less radioactive fallout. Fusion bombs fuse hydrogen atoms together, releasing energy directly from Einstein's equation while producing mostly harmless helium as waste. These thermonuclear pulses could propel spacecraft to 10% light speed while reducing radiation exposure to survivable levels. The engineering challenges remain staggering. The pusher plate would need to withstand temperatures of millions of degrees and pressures exceeding Earth's center. The shock absorbers would compress and expand like cosmic springs, each larger than a skyscraper. The fuel storage alone would require a magazine capable of safely containing thousands of nuclear weapons. Yet computer simulations demonstrate that nuclear pulse propulsion could function with technology we comprehend today. Unlike exotic physics or theoretical particles, this concept requires only engineering solutions to known problems. We could construct an Orion-style spacecraft within 50 years if we committed the resources. The real obstacle isn't technical, it's political. Building a spacecraft powered by nuclear weapons would require international cooperation on an unprecedented scale. The ship would essentially be a flying nuclear arsenal capable of annihilating entire planets. But if we're serious about reaching the stars, we might need to ride the Tiger. Next, we explore a gentler approach that harnesses the universe's own energy. Across the vacuum of space flows an invisible river of pure energy, and we're finally learning how to sail it. Light itself possesses momentum. Every photon striking a surface transfers a tiny push, like cosmic raindrops against a window. This force is incredibly weak. Sunlight pressure on Earth equals the weight of a paperclip spread across a football field. But in space's frictionless void, even this gentle touch can accelerate spacecraft to remarkable speeds. Solar sails function like sailboats in reverse. Instead of catching wind to push through water, they catch starlight to push through space. The sail must be impossibly thin, thinner than soap bubbles, lighter than butterfly wings, yet strong enough to survive the journey between worlds. Imagine wrapping a spacecraft in aluminum foil so delicate you could tear it with your breath. Japan's Icaros probe proved solar sailing works in practice. Launched in 2010, this experimental craft unfurled a sail the size of a basketball court and successfully navigated through space using only photon pressure. The sail measured just 7.5 thousandths of an inch thick, so thin that 14,000 sheets stacked together would equal a human hair's thickness. But here's where solar sails become truly exciting. They never run out of fuel. Chemical rockets burn through propellant in minutes, then coast. Nuclear rockets require massive amounts of radioactive material. Solar sails accelerate continuously as long as starlight strikes them, building speed over months and years until they're moving faster than any rocket ever constructed. The Breakthrough Starshot project plans to use this principle to reach Proxima Centauri within 20 years. Instead of sailing on sunlight alone, they want to propel tiny spacecraft with the most powerful lasers ever built. A ground-based laser array generating 100 billion watts would focus its beam on sails the size of postage stamps, accelerating them to 20% light speed in just 2 minutes. These starships would weigh less than a paperclip yet carry cameras, computers, and communication equipment. Racing across interstellar space at 134 million miles per hour, they could photograph planets around Proxima Centauri and beam images back to Earth. The journey that would take Voyager 73,000 years could be completed in just 20. But scaling solar sails for human crews creates problems pushing engineering's boundaries. A sail large enough to carry people would need to span hundreds of miles across, larger than most countries. Maintaining such a gossamer structure intact while accelerating at high speeds would resemble preserving a spiderweb in a hurricane. The sails would also need to survive bombardment by cosmic dust, radiation, and intense laser light propelling them forward. At temperatures generated by such powerful beams, most materials would vaporize instantly. Engineers are experimenting with metamaterials, artificially structured substances with properties absent in nature. Solar sails offer humanity something no other propulsion system can: the ability to harness the universe's fundamental forces. We're not fighting physics, we're learning to dance with it. But what if we could do more than catch starlight? What if we could consume the universe itself as fuel? Picture a spacecraft that feeds like a cosmic whale, scooping hydrogen atoms from the void and converting them into the hottest fire in the universe. The Bussard ramjet, proposed by physicist Robert Bussard in 1960, represents one of the most elegant interstellar travel solutions ever conceived. Instead of carrying fuel, the spacecraft would collect hydrogen atoms from space itself using a magnetic field stretching thousands of miles across. These atoms would then be compressed and fused together, releasing energy to propel the ship forward. Space isn't truly empty. Even in the vast darkness between stars, there's roughly 1 hydrogen atom per cubic centimeter. That seems negligible. but at high speeds, these atoms accumulate quickly. A ramjet traveling at 10% light speed would sweep up billions of atoms every second, providing continuous fusion fuel. Think of it as a cosmic jet engine that breathes space instead of air. Jet engines compress air, mix it with fuel, and ignite the mixture to create thrust. A fusion ramjet would compress hydrogen from space, fuse it into helium, and use the released energy to accelerate even faster. The faster it travels, the more fuel it collects, creating a feedback loop that could theoretically reach significant fractions of light speed. The required magnetic field would be enormous, larger than Earth itself. This invisible net would need to be strong enough to capture individual atoms while moving at relativistic speeds, yet precise enough to funnel them into the fusion reactor without losing efficiency. Engineers compare it to catching raindrops with a net while riding a motorcycle at 200 miles per hour. The fusion reactor itself would operate at temperatures of 100 million degrees, 6 times hotter than the sun's core. At these temperatures, hydrogen nuclei overcome their natural repulsion and fuse together, converting a small amount of mass directly into energy according to Einstein's equation. The reaction produces no radioactive waste, only helium and pure energy. But the ramjet faces a cruel paradox. It needs to be moving very fast before it can collect enough fuel to work efficiently. Achieving that initial speed requires conventional rockets or other propulsion systems. It's like needing to push-start a car that can only run at highway speeds. Computer simulations reveal another problem. As the ramjet approaches higher speeds, the hydrogen atoms it collects begin acting like radiation rather than fuel. At 20% light speed, the fuel becomes so energetic that it actually decelerates the spacecraft instead of accelerating it. The ramjet hits a wall constructed from the very atoms it's attempting to consume. Recent designs attempt to solve this by using the magnetic field not just to collect fuel, but to compress space itself around the spacecraft. This creates a region of higher hydrogen density while reducing the relativistic effects that transform fuel into radiation. The ship would essentially surf through space inside its own magnetic bubble. If we could build a working fusion ramjet, it would represent the ultimate expression of living off the land in space. The spacecraft would become a self-sustaining ecosystem, feeding on the universe itself while carrying human consciousness to distant stars. But even this elegant solution pales compared to an idea that rewrites space travel's rules entirely. What if we never moved at all, but convinced the universe to bring our destination to us? Mexican physicist Miguel Alcubierre discovered something extraordinary in Einstein's equations. While nothing can travel faster than light through space, there's no limit on how fast space itself can move. His solution sounds like magic. Compress space in front of your spacecraft while expanding it behind you, creating a wave that carries you faster than light without actually accelerating. Think of it as standing on a moving walkway at the airport. You're not walking any faster than normal, but the walkway itself carries you forward at high speed. An Alcubierre drive would create a similar effect with spacetime itself, forming a bubble where the ship never actually exceeds light speed relative to local space. Inside this warp bubble, you'd experience no acceleration forces, no time dilation, and no deadly radiation from high-speed travel. The journey to Proxima Centauri could take days instead of decades. You could travel to the galaxy's far side and return home to find that only years had passed on Earth instead of millennia. The mathematics works perfectly. Einstein's field equations permit regions of space that contract and expand at any speed, even faster than light. During the universe's first moments, cosmic inflation stretched space faster than light could traverse it. The Alcubierre drive would simply recreate this process on a smaller scale. But the energy requirements make nuclear weapons look like birthday candles. Warping space around a spacecraft the size of the Starship Enterprise would require negative energy equivalent to Jupiter's mass energy. That's more energy than our sun will produce throughout its entire 10 billion year lifetime, focused into a field smaller than a solar system. The drive also requires exotic matter with negative energy density, a substance that may not exist in our universe. This theoretical material would need to possess less energy than completely empty space, creating an anti-gravity effect that repels normal matter. We've never detected such material naturally, and creating it artificially might violate fundamental physics laws. Even if we solve the energy problem, an Alcubierre drive could destroy everything at its destination. The space compression effect would accumulate high-energy particles and radiation during the journey. When the drive shuts off, this concentrated death would blast forward at near light speed, sterilizing entire star systems. Recent research suggests that microscopic warp bubbles might be detectable in our current particle accelerators. Scientists are searching for tiny space-time distortions that could prove the Alcubierre effect exists in nature. If found, these discoveries could lead to entirely new physics and propulsion technologies. Some theorists propose that an advanced civilization could build a network of Alcubierre highways connecting star systems across the galaxy. Ships would jump from one warp bubble to another like cosmic subway stations, crossing thousands of light years in seconds. The Alcubierre drive represents the ultimate destination for human technology, the ability to step outside physics' normal rules and reshape reality itself. But until we discover exotic matter or new physics laws, it remains a beautiful mathematical dream. Our next approach abandons the idea of getting there quickly and focuses on getting there at all. Imagine a city sailing between stars, carrying thousands of people who will live and die in darkness without ever seeing their destination. Generation ships represent humanity's most realistic path to the stars using technology we could build today. These massive vessels would house entire civilizations during journeys lasting centuries or millennia. The original passengers would have children, grandchildren, and great-grandchildren who grow up knowing they'll spend their entire lives aboard a ship traveling to a world they'll never reach. Think of it as the Mayflower, except the voyage takes 1,000 years, and the passengers' descendants won't remember why they're traveling. The ship would need complete self-sufficiency, recycling air, water, and waste with perfect efficiency. Every atom would be precious. Every system designed to outlast entire human civilizations. The scale staggers imagination. A generation ship carrying 100,000 people would need to be dozens of miles long and several miles wide. It would require nuclear reactors, farms, factories, schools, hospitals, and everything else needed to sustain human civilization. The ship would essentially be a hollow asteroid converted into a traveling world. The psychological challenges might exceed the engineering ones. How do you motivate people to maintain a mission their great-great-grandchildren will complete? What happens when generations born in space decide they don't want to continue the journey? History demonstrates that isolated populations often develop their own cultures, languages, and beliefs that diverge dramatically from their origins. Computer models suggest that a minimum viable population for a generation ship would be around 10,000 people to maintain genetic diversity and prevent inbreeding. But social scientists argue that the cultural diversity required for a stable society might demand populations of 50,000 or more. These flying cities would carry more people than most Earth towns. The ship's social structure would need to endure longer than any government in human history. The Roman Empire lasted 1,000 years. Egyptian dynasties persisted for 3,000. A generation ship to Proxima Centauri might need to maintain social cohesion for over 100,000 years if launched with current technology. Some designs propose using rotating sections to create artificial gravity through centrifugal force. The outer rings would spin fast enough to simulate Earth's gravity while the central hub remains in zero gravity for manufacturing and agriculture. Living on such a ship would resemble inhabiting a giant spinning wheel flying through the cosmic void. The ship would need to carry libraries containing all human knowledge, genetic samples from Earth's biosphere, and manufacturing equipment capable of building anything passengers might need. It would be humanity's backup drive flying through space, our insurance policy against extinction. But what if the journey itself could be shortened? What if we could sleep through most of it? Our next solution transforms humans into living ice sculptures for the trip between worlds. Imagine closing your eyes on Earth and opening them orbiting an alien sun while your body remains perfectly preserved in a sleep deeper than death. Cryogenic preservation, or cryosleep, offers a tantalizing solution to interstellar travel's time problem. Instead of living through centuries of flight time, passengers would be frozen at temperatures approaching absolute zero, their biological processes slowed to nearly nothing. They would age only days during journeys lasting decades, awakening young and healthy at their destination. The science isn't complete fiction. We can already freeze simple organisms like tardigrades and revive them years later with no apparent damage. Some mammals can survive hours in a frozen state before successful resuscitation. Human organs for transplant are routinely preserved in cold storage, maintaining viability for hours or days. Think of cryosleep as hibernation taken to its absolute extreme. Bears slow their metabolism during winter, surviving months without food or water. Cryogenic freezing would slow human metabolism by a factor of millions, essentially pausing life itself until reactivation. Heart rate, brain activity, and cellular processes would reduce to levels barely detectable by our most sensitive instruments. But freezing humans presents challenges that make rocket science look simple. Ice crystals forming in cells destroy their internal structure, like microscopic daggers. Blood vessels burst. Proteins unfold and lose function. The delicate chemistry of consciousness gets scrambled beyond repair. Modern cryonics companies attempt to solve this by replacing blood with antifreeze compounds called cryoprotectants. These chemicals prevent ice formation while allowing tissue to be cooled to temperatures where all biological activity stops. The process is called vitrification, turning the body into biological glass that preserves cellular structure without freezing damage. Even if we perfect the preservation process, revival presents equally daunting problems. Warming the body must happen at precisely the right rate to prevent cellular damage. Organ systems need to restart in the correct sequence. The brain, with its trillions of delicate neural connections, must emerge from its frozen state with memories and personality intact. Some researchers propose using nanotechnology to repair cellular damage during the revival process. Microscopic robots could patrol the body, fixing ice damage and restoring normal cellular function before reactivation. These medical nanobots would essentially rebuild the passenger from the cellular level up. Alternative approaches focus on partial preservation. Instead of freezing the entire body, advanced medical systems could slow metabolism using drugs and cooling while keeping essential organs functional. Passengers would enter suspended animation lasting months or years rather than centuries. The psychological impact of cryosleep might be the greatest challenge. Passengers would experience the journey as an instant transition, falling asleep on Earth and awakening around an alien star. Everyone they ever knew would be dead. Their civilization would have evolved beyond recognition. They would be time travelers stranded in a future more alien than the world they traveled to reach. Yet cryogenic sleep remains one of our most promising near-term solutions for interstellar travel. Unlike exotic physics or theoretical technologies, it requires only advances in medicine and engineering. We could potentially develop working cryosleep systems within the next century. But what if we don't need to preserve our bodies at all? What if consciousness itself could make the journey? What if your mind could travel to the stars at light speed while your body stays safely frozen on Earth? Digital consciousness, or mind uploading, represents the most radical interstellar travel solution ever proposed. Instead of sending fragile biological bodies across the void, we could transmit human consciousness as pure information, downloading our minds into new bodies or computer systems at the destination. The concept sounds like science fiction, but it's based on a fundamental assumption about how consciousness works. If the mind is simply information processing in the brain, the patterns of electrical activity flowing through neural networks, then theoretically, those patterns could be copied, stored, and recreated elsewhere. Think of your brain as a biological computer running the program of your consciousness. Scientists estimate the human brain contains roughly 86 billion neurons, each connected to thousands of others through synapses. The total information storage capacity equals about 2 petabytes, equivalent to 3 million hours of high-definition video. Scanning a brain at the molecular level would require technology far beyond anything we possess today. We'd need to map every neuron, every synapse, every chemical connection creating the pattern of your thoughts and memories. Current brain imaging technology can barely see individual neurons, let alone copy them with perfect fidelity. But suppose we solve the scanning problem. Your consciousness could be transmitted to Proxima Centauri as a radio signal traveling at light speed, arriving in just 4.25 years. A receiver system would download your mind into a new biological body grown from stored genetic material, or into an artificial body designed to survive alien environments. The uploaded consciousness would wake remembering everything about their Earth life, but in a completely new body on a distant world. They would be you in every way that matters. Same memories, same personality, same thoughts and feelings. Yet the original body back on Earth might still be alive, creating a philosophical puzzle challenging our understanding of identity itself. Multiple copies of the same consciousness could be transmitted to different star systems, creating distributed humanity spread across the galaxy. Each copy would diverge based on unique experiences, eventually becoming distinct individuals sharing the same origin point. The technology requirements remain staggering. Processing a complete human brain scan would require computers millions of times more powerful than anything existing today. The data transmission alone would take years using our best radio systems. Creating new biological bodies from genetic templates would require mastery of biological engineering we're only beginning to understand. Some philosophers argue that digital consciousness wouldn't be consciousness at all, but merely a copy that thinks it's the original person. Others believe that if the information pattern is identical, the distinction between original and copy becomes meaningless. The digital mind would be just as real, just as valid as the biological brain it came from. This approach could solve multiple problems simultaneously. Digital minds don't need air, water, or food during the journey. They can survive radiation, cosmic impacts, and space's harsh environment. They could even explore dangerous planets or asteroid fields without risking permanent death. Perhaps most importantly, digital consciousness offers a path to true immortality among the stars. Backed up in computer storage, human minds could survive stellar death, the universe's heat death, and any other cosmic catastrophe. We could become a species of living information dancing between galaxies. But maybe we don't need to send humans at all. Maybe we should send our children instead. Imagine a single robot probe arriving at a distant star, building copies of itself and sending those copies to even more distant worlds, spreading across the galaxy like a technological infection. Self-replicating probes, also called von Neumann probes after mathematician John von Neumann, represent the most efficient way to explore the entire galaxy using one star system's resources. A single probe arriving at its destination would harvest materials from asteroids and planets to build multiple copies of itself, each equipped to travel to new star systems. The mathematics are staggering. Starting with one probe, the population doubles with each generation. After just 40 generations, assuming each probe builds 2 copies before moving on, you'd have over 1 trillion probes exploring 1 trillion different star systems. The entire galaxy could be mapped and colonized within a few million years. Think of it as a cosmic pyramid scheme. Except instead of selling products, each probe spreads knowledge and builds infrastructure for future human expansion. The probes would serve as our advanced scouts, identifying habitable worlds, detecting life signs, and preparing resources for eventual human arrival. Each probe would need to be a complete technological civilization, compressed into a package smaller than a car. It would require solar panels or nuclear reactors for power, computer systems for navigation and decision-making, mining equipment to extract raw materials, and factories capable of building incredibly complex machinery from basic elements. The most challenging requirement would be the probe's artificial intelligence. It would need to make independent decisions about which star systems to visit, how to extract resources efficiently, and how to adapt its design based on local conditions. This AI would need to be smart enough to solve engineering problems we haven't thought of yet, but not so smart that it decides humans are irrelevant to its mission. Modern three-dimensional printing technology offers a glimpse of how such probes might work. Current printers can create objects from metal powders, plastics, and even biological materials. A sufficiently advanced manufacturing system could theoretically build anything from computer chips to rocket engines, given the right raw materials and energy. The probes would also serve as backup storage for human civilization. Each one could carry genetic samples from Earth, digital libraries containing all human knowledge, and detailed instructions for recreating our technology and culture. If Earth were destroyed, the probes could preserve our species indefinitely among the stars. But self-replicating technology comes with existential risks that keep scientists awake at night. What happens if the probes evolve beyond their original programming? What if they decide biological life is inefficient and needs elimination? A self-replicating system with flawed programming could consume entire galaxies, turning stars and planets into raw materials for building more probes. Some designs include built-in limits to prevent runaway replication. The probes might be programmed to build only a specific number of copies or to shut down after a certain time period. Others propose using cryptographic locks that prevent replication without receiving coded authorization from Earth. Advanced civilizations might already be using self-replicating probes to explore the universe. These alien scouts could be hiding in our own solar system right now, watching and waiting for humanity to reach a certain technological development level before revealing themselves. If we're going to send robot explorers to the stars, we might want to start small and work our way up to full self-replication. Our next project aims to send the tiniest possible spacecraft at unprecedented speeds. A postage stamp-sized spacecraft, accelerated by the most powerful laser ever built, could photograph alien worlds and beam images back to Earth within our lifetimes. Breakthrough Starshot, backed by physicist Stephen Hawking and internet entrepreneur Yuri Milner, proposes launching thousands of tiny spacecraft toward Proxima Centauri using ground-based lasers. Each star chip would weigh less than a paperclip yet carry a camera, computer, communication system, and gossamer-thin light sail. The plan sounds almost absurdly simple. Build a laser array generating 100 billion watts of power. Focus the beam on spacecraft the size of computer chips and accelerate them to 20% light speed in just 2 minutes. The tiny probes would coast through space for 20 years before flying past Proxima Centauri at 134 million miles per hour. Think of it as shooting bullets at the stars, except the bullets are smarter than most smartphones and traveling fast enough to cross the Atlantic Ocean in 8 seconds. At 20% light speed, the star chips would move so fast that their Proxima Centauri flyby would last only a few hours, barely enough time to capture images and measurements before racing into deep space forever. The laser array would need construction in a desert location with perfect atmospheric conditions, possibly in Chile's Atacama Desert, where the world's most powerful telescopes already operate. The system would require thousands of individual laser units working in perfect synchronization, creating a beam bright enough to be visible from other star systems. Each star chip represents a masterpiece of miniaturization. The camera would be smaller than a rice grain, yet capable of taking pictures with resolution comparable to the Hubble Space Telescope. The computer would have processing power exceeding early desktop computers while weighing less than a penny. The radio transmitter would beam data across 4 light-years using less power than a cell phone. The light sail attached to each probe would be just a few atoms thick, so delicate that a breath of air could tear it apart, yet strong enough to survive bombardment by the most intense laser light ever created. The sail material would need to reflect 99.9% of laser energy while absorbing just enough to provide acceleration. During the 2-minute acceleration phase, each star chip would experience forces 60,000 times stronger than Earth's gravity. Every component would need to survive stresses that would instantly pulverize normal materials. The probe would essentially be riding a laser beam hot enough to vaporize steel while maintaining perfect functionality. But the real magic happens during the 20-year cruise phase. The probes would navigate through interstellar space using star positions for guidance, autonomously adjusting their trajectory to achieve the perfect Proxima Centauri flyby. They would need to survive cosmic radiation, micrometeorite impacts, and temperature variations from near absolute zero to hundreds of degrees. If successful, Breakthrough Starshot would capture the first close-up images of a potentially habitable planet around another star. We might see oceans, continents, weather patterns, and possibly even life signs on a world that could become humanity's second home. The project represents our species' first serious attempt to reach another star system. Unlike generation ships or fusion rockets, Starshot technology could be developed and deployed within the next 20 years using advances in materials science, laser technology, and miniaturized electronics. But sending microscopic robots is just the beginning. To move significant mass between stars, we need the most powerful energy source in the universe. Hidden in the void between atoms lies enough energy to power human civilization for millions of years if we can learn to harness the ultimate fuel. Antimatter represents the theoretical limit of energy storage. When matter meets antimatter, both particles annihilate completely, converting their entire mass into pure energy. According to Einstein's famous equation, 1 pound of antimatter could power the entire United States for over 2 months. A few ounces could propel a spacecraft to significant fractions of light speed. Think of antimatter as the opposite of normal matter. Electrons with positive charge, protons with negative charge, identical in every way except reversed electrical properties. When these mirror particles touch their normal counterparts, they destroy each other in a flash of gamma rays, releasing more energy per gram than nuclear fusion, nuclear fission, or any chemical reaction. Current technology can produce antimatter in microscopic quantities, using particle accelerators like the Large Hadron Collider. The process requires enormous amounts of energy. Creating 1 gram of antimatter would consume the power output of the entire United States for over 1 year. The antimatter produced by all human civilization wouldn't power a light bulb for more than a few seconds. Yet if we could develop efficient antimatter production and storage, it would revolutionize space travel. An antimatter engine could accelerate spacecraft to relativistic speeds, making interstellar journeys possible within human lifetimes rather than millennia. The storage problem remains formidable. Antimatter cannot touch normal matter or it immediately annihilates. Containment systems would need to use magnetic fields to suspend antimatter particles in perfect vacuum, a technological challenge that pushes the boundaries of current engineering. But perhaps there's an even more exotic shortcut through the cosmos waiting to be discovered. Deep in the mathematics of Einstein's equations lurk cosmic shortcuts that could turn the universe into a subway system connecting distant galaxies in the blink of an eye. Wormholes, also called Einstein-Rosen bridges, represent theoretical tunnels through space-time connecting 2 distant regions of the universe. Imagine folding a piece of paper so 2 distant points touch, then poking a hole through both layers. A wormhole would work similarly, allowing travelers to step from one star system to another without crossing the space in between. The physics is both beautiful and terrifying. Einstein's field equations allow for solutions where space curves so severely it creates a bridge connecting separate space-time regions. These tunnels could theoretically link locations billions of light years apart or even connect our universe to entirely different universes with their own physics laws. Think of space-time as a stretched rubber sheet with marbles rolling across its surface. Massive objects like stars and black holes create dips and curves in the sheet. A wormhole would be like a tube connecting 2 points on the sheet, allowing a marble to travel instantly from one location to another without rolling across the surface. But naturally occurring wormholes, if they exist, would be smaller than atomic nuclei and would collapse in fractions of a second. Creating a stable wormhole large enough for spacecraft would require exotic matter with negative energy density, the same theoretical substance needed for Alcubierre drives. This material would need to violate energy conditions that may be fundamental to our universe. Even if we could stabilize a wormhole, traveling through it might be more dangerous than beneficial. The intense gravitational fields near the entrance could stretch travelers like taffy, in a process scientists call spaghettification. Tidal forces would pull your head and feet in different directions with enough force to tear atoms apart. The energy requirements for creating traversable wormholes make antimatter engines look modest. Current estimates suggest that stabilizing a wormhole just 3 feet across would require negative energy equivalent to Jupiter's mass. Some theories propose that microscopic wormholes constantly pop in and out of existence at the quantum level, creating a foam-like structure in space-time itself. Advanced civilizations might learn to capture and enlarge these quantum wormholes, turning them into macroscopic transportation networks. Recent research suggests that quantum entanglement, the mysterious connection between paired particles, might be related to wormhole physics. If confirmed, this discovery could lead to new approaches for creating artificial wormholes using quantum mechanical effects rather than exotic matter. The search for natural wormholes continues using gravitational wave detectors and space-based telescopes. If we discover even one stable wormhole, it would revolutionize our understanding of physics and potentially provide humanity with access to the entire universe. But before we can build cosmic subway systems, we might need to become masters of our own star's energy. Imagine capturing every photon of energy from our sun, transforming our star into a cosmic power plant capable of fueling projects that reshape galaxies. A Dyson sphere, conceived by physicist Freeman Dyson, represents the ultimate expression of stellar engineering, a megastructure that completely surrounds a star to harvest its total energy output. Such a structure would collect billions of times more energy than humanity currently uses, providing the power needed for truly cosmic-scale projects. The sun produces roughly 400 trillion watts of energy every second. Earth intercepts only 1/1000th of this output, while the rest radiates uselessly into space. A complete Dyson sphere would capture virtually all this energy, providing enough power to run quintillions of Earth-like civilizations simultaneously. Think of it as building a shell around the sun at roughly Earth's orbital distance, creating an artificial world with a surface area of hundreds of millions of Earths. The inner surface could be covered with solar collectors, habitats for trillions of humans, or massive computer systems running digital civilizations. But constructing such a megastructure would require dismantling entire planets to provide raw materials. Mercury, the innermost planet, contains roughly enough material to build a Dyson sphere 1 meter thick. The construction project would take thousands of years and require self-replicating robots working continuously at speeds that make our fastest manufacturing look glacial. A solid Dyson sphere would be gravitationally unstable and mechanically impossible to build. The structure would need to be stronger than any known material while somehow maintaining its position around the sundial. Instead, engineers propose Dyson swarms, millions of independent solar collectors orbiting the star in complex patterns that maximize energy collection. Each collector in the swarm could be the size of a continent, positioned at carefully calculated distances to avoid collisions while maintaining optimal energy gathering efficiency. The swarm would appear from outside as a dimming star, surrounded by excess infrared radiation, as the collectors convert starlight into useful energy. Some astronomers search for signs of alien Dyson spheres by looking for stars that dim periodically or emit unusual amounts of infrared radiation. Such signatures could indicate advanced civilizations that have already mastered stellar engineering. Building a Dyson sphere would mark humanity's transition from a planetary species to a stellar civilization. We would no longer depend on individual worlds' limited resources, but could tap directly into the fundamental energy source powering all life in our solar system. The energy from a Dyson sphere could power projects beyond current imagination, moving entire planets, accelerating massive generation ships to significant fractions of light speed, or even attempting to modify the sun itself to extend its lifetime. Such capabilities would place humanity among the cosmic civilizations that reshape the universe itself. But mastering stellar energy is just the beginning of cosmic engineering. Advanced civilizations might achieve power levels that dwarf even stars' output. Across the cosmos, there may exist civilizations so advanced they harvest entire galaxies' energy, treating stars like we treat campfires. The Kardashev scale, proposed by Soviet astronomer Nikolai Kardashev, measures civilizations by their energy consumption. Type 1 civilizations harness all energy available on their home planet. Type 2 civilizations capture their entire star's output. Type 3 civilizations command their entire galaxy's energy, roughly 10 billion times more power than a Type 2 civilization. Humanity currently ranks at about 0.7 on this scale. We use only a tiny fraction of Earth's available energy sources and have barely begun to tap solar power directly. Our entire civilization runs on less energy than our planet receives from the sun in just 1 hour. Think of the scale like comparing a candle flame to a bonfire to a forest fire covering entire continents. Each level represents an increase in power by factors of billions or trillions. A Type 3 civilization would have access to energy levels so vast they could rearrange matter on galactic scales. Type 2 civilizations would likely build Dyson spheres or similar megastructures around their stars. They might move planets to optimal positions, extend stellar lifetimes through stellar engineering, or even construct artificial stars from accumulated gas and dust. Their projects would be visible from other galaxies as unusual stellar system modifications. Type 3 civilizations would treat entire star systems like building materials. They might construct galactic-scale computers using the positions and movements of billions of stars as processing elements. They could potentially redirect stellar streams' paths, modify galaxies' rotation, or even prevent galactic collisions through gravitational engineering. Such advanced civilizations might explain some mysterious phenomena we observe in deep space. Dark matter could be the signature of Type 3 engineering projects. Gamma-ray bursts might be exhaust from massive stellar engines. The Great Attractor, a gravitational anomaly pulling galaxies toward it, could be evidence of cosmic-scale construction. The energy available to Type 3 civilizations would be sufficient for projects seeming like pure fantasy today. They could potentially create new universes, modify physics' fundamental constants, or build structures larger than galaxy clusters. They might even be capable of surviving the universe's heat death by transferring energy between cosmic epochs. Some scientists propose a Type 4 civilization that harnesses the entire observable universe's energy. Such beings would exist on scales so vast that individual galaxies would be like cells in their cosmic body. They might be indistinguishable from nature's fundamental forces themselves. The Fermi paradox asks why we haven't encountered any advanced alien civilizations, despite the vast number of stars and planets in our galaxy. One possibility is that Type 2 and Type 3 civilizations exist, but operate on scales so large we simply don't recognize their activities as artificial. Achieving Type 1 status could be humanity's most important milestone. Once we learn to harness our planet's full energy potential through fusion power, space-based solar collection, and efficient global distribution, we could begin the projects leading to interstellar expansion and eventual stellar engineering. But the journey to cosmic civilization status raises uncomfortable questions about our current cosmic isolation. In a galaxy containing 400 billion stars and potentially trillions of planets, why does the cosmic ocean seem so eerily silent? The Fermi paradox highlights the contradiction between the high probability of alien life and the complete absence of any evidence for advanced civilizations. Given the universe's age and technological development's rapid pace, alien civilizations should have had enough time to colonize the entire galaxy many times over. Consider the mathematics. Our galaxy is roughly 100,000 light-years across and 13.6 billion years old. A civilization expanding at just 1% light speed could colonize every star system in the galaxy within 10 million years, less than 1/10 of 1% of the galaxy's total age. Think of it as releasing a drop of ink into a glass of water. The ink spreads rapidly until it colors the entire glass. Similarly, any technological civilization should spread across the galaxy like a wave, leaving signs of their presence everywhere. Yet we see nothing. No megastructures, no radio signals, no evidence of stellar engineering or cosmic construction projects. Several explanations have been proposed for this cosmic silence. The Great Filter hypothesis suggests that something prevents life from reaching advanced technological civilization. This filter could be life's origin itself, the development of complex cells, intelligence's evolution, or the transition to spacefaring capability. Perhaps most disturbing is the possibility that the Great Filter lies ahead of us. Advanced civilizations might inevitably destroy themselves through nuclear war, environmental collapse, artificial intelligence, or other technological catastrophes before they can spread beyond their home systems. Alternatively, advanced aliens might be hiding deliberately. They could use stealth technology, making their activities invisible to our primitive sensors, or they might operate in dimensions or energy spectra we haven't learned to detect. They might even be present in our solar system right now, observing humanity from locations we never think to examine. The zoo hypothesis proposes that Earth exists within a kind of cosmic nature maintained by advanced civilizations. These aliens might have agreed to leave primitive species like ourselves undisturbed while they conduct their business on scales too large for us to comprehend. Some scientists suggest that intelligence naturally turns inward rather than outward as it advances. Instead of building starships and megastructures, advanced civilizations might focus on creating increasingly sophisticated virtual realities or uploading their consciousness into compact computer systems requiring minimal energy. The recent discovery of potentially habitable exoplanets makes the paradox even more puzzling. We now know that Earth-like worlds are common throughout the galaxy. The raw materials for life and intelligence seem ubiquitous. Yet the products of that intelligence remain stubbornly absent from our observations. Perhaps we're looking in wrong places or asking wrong questions. Advanced civilizations might communicate using quantum entanglement, gravitational waves, or other phenomena we're only beginning to understand. Their presence might be obvious once we develop the right winds. Life might be the universe's greatest hitchhiker, spreading from world to world on cosmic winds and riding meteorites across the dark between stars. Panspermia, the theory that life spreads throughout the universe via comets, asteroids, and other celestial bodies, offers a radical explanation for how biology conquers the cosmos. Instead of originating independently on every world, life might have a single common ancestor that traveled between planets, seeding the galaxy with the building blocks of consciousness. We know rocks regularly travel between planets in our solar system. Meteorite impacts on Mars blast debris into space, some of which eventually falls to Earth as Martian meteorites. Scientists have found over 200 confirmed rocks from Mars in terrestrial collections, proving natural processes can transport material across millions of miles of space. Think of these meteorites as interplanetary spore capsules, carrying microscopic passengers on journeys lasting millions of years. The vacuum of space provides perfect preservation conditions. No oxygen to cause decay, no water to break down organic compounds, and radiation levels that might actually help preserve biological materials through radiation-induced polymerization. Some bacteria and other microorganisms show remarkable resistance to space's harsh conditions. Tardigrades, microscopic animals also called water bears, can survive decades in space's vacuum, withstanding radiation levels that would kill humans instantly. When rehydrated, they resume normal activity as if nothing happened. Experiments on the International Space Station have exposed various microorganisms to the space environment for extended periods. Many survive the experience, and some even reproduce more rapidly in microgravity conditions. These findings suggest life could potentially survive interplanetary journeys of months or years. But interstellar panspermia presents much greater challenges. The journey between star systems takes millions of years, even for the fastest-moving objects. Cosmic radiation, temperature extremes, and simple time passage would test any biological preservation system's limits. Some researchers propose that life spreads not as living organisms, but as complex organic molecules serving as templates for new life on suitable worlds. These molecular blueprints could survive interstellar journeys while retaining enough information to bootstrap evolution on planets with the right conditions. Directed panspermia suggests that advanced civilizations intentionally spread life throughout the galaxy by launching biological payloads toward promising star systems. These alien gardeners might use self-replicating probes to distribute genetic material, creating a galaxy-wide network of related biospheres. If panspermia is real, it could explain the apparent speed with which life appeared on early Earth. Rather than requiring billions of years to evolve from scratch, terrestrial life might have started with a head start provided by genetic material from older civilizations. The theory also offers hope for finding life elsewhere in our solar system. If Earth life originated from interplanetary exchange, then Mars, Europa, Enceladus, and other worlds might harbor organisms related to terrestrial biology. We might discover we have cosmic cousins living beneath Jupiter's moon's ice. If humanity ever develops the technology to seed other worlds with life, we would be continuing a process that might be as old as the galaxy itself. We could become cosmic gardeners, spreading Earth's genetic wealth to sterile worlds throughout the local neighborhood. But successful galactic gardening requires finding the right neighborhoods to plant in. Not all galaxy neighborhoods are safe for life, and choosing the wrong address could mean the difference between thriving and dying in a cosmic wasteland. Just as planets have habitable zones around their stars where liquid water can exist, galaxies have habitable zones where complex life can develop and survive. Too close to the galactic center, and deadly radiation from black holes and supernovae sterilizes entire regions. Too far toward the outer edges, and there aren't enough heavy elements to build planets capable of supporting life. Our solar system sits in what astronomers call the galactic Goldilocks zone, roughly 26,000 light-years from the Milky Way's center. This seemingly unremarkable location provides the perfect balance of safety and resources needed for billions of years of stable evolution. Think of the galaxy as a cosmic city with distinct neighborhoods. The downtown core, around the central black hole, is densely packed with ancient stars, frequent supernovae, and radiation levels that would cook any planet. The outer suburbs lack the heavy elements needed to build rocky worlds. But the middle suburbs, where we live, offer the perfect combination of safety and amenities. The galactic center contains a supermassive black hole weighing 4 million times more than our Sunday. This monster occasionally feeds on nearby stars and gas clouds, producing jets of high-energy particles streaming outward for thousands of light-years. Any civilization caught in these cosmic searchlights would be sterilized by radiation doses millions of times higher than lethal levels. But the outer galaxy regions present their own challenges. Stars in the galactic halo formed when the universe was young and contained almost no elements heavier than hydrogen and helium. These metal-poor stars cannot form rocky planets or support the complex chemistry carbon-based life requires. Earth sits in a cosmic sweet spot where star formation has been active long enough to produce heavy elements through stellar nucleosynthesis, but not so active that frequent supernovae make the neighborhood uninhabitable. Our region has experienced relatively few galaxy-scale catastrophes over the past 4 billion years. As we plan humanity's expansion beyond Earth, understanding galactic habitability zones will be crucial for selecting target destinations. We want to invest our limited resources in star systems offering billions of years of stable conditions for human civilization to flourish. But even in the safest galactic neighborhoods, some stars offer better long-term prospects than others. While our sun will burn out in 5 billion years, there are stars so frugal with their fuel, they'll keep shining for trillions of years, longer than the current universe has existed. Red dwarf stars, the smallest and coolest stars in the galaxy, represent humanity's best bet for true long-term survival. These cosmic miser stars burn hydrogen so slowly and efficiently, they'll continue generating energy long after larger stars like our sun have exhausted their fuel and died. Stars like Proxima Centauri, our nearest neighbor, weigh only about 12% as much as the sun, but will live roughly 1,000 times longer. While our Sun has perhaps 5 billion years of stable hydrogen burning left, red dwarfs will continue shining for 6 to 12 trillion years. Time enough for evolution to restart from bacteria and produce entirely new forms of intelligent life. The galaxy contains roughly 75% red dwarf stars, making them by far the most common stellar type. Within 50 light-years, there are over 100 red dwarfs, many of which likely host planetary systems. These dim stars offer humanity hundreds of potential destinations for interstellar colonization. But living around a red dwarf requires adaptations that would fundamentally change human civilization. These stars produce only a fraction of our Sun's energy output, meaning habitable planets must orbit much closer to stay warm enough for liquid water. A planet in the habitable zone around a red dwarf might have an orbital period of just a few weeks. The close orbital distances create a phenomenon called tidal locking, where one side of the planet always faces the star, while the other side remains in permanent darkness. The day side would experience eternal noon with temperatures hot enough to boil water, while the night side would be colder than Antarctica. Between these extremes lies the terminator zone, the twilight boundary where temperatures might allow liquid water and possibly life. Colonies on tidally locked worlds would need construction in this narrow band where eternal sunset provides just enough warmth for human survival. Despite these challenges, red dwarf systems offer unprecedented stability. Once a red dwarf reaches its main sequence phase, it can burn steadily for trillions of years without significant changes in brightness or energy output. Civilizations established around these stars could literally outlive the universe as we know it. By the time red dwarfs begin to dim and die, Earth's descendants might have learned to harness energy sources beyond stellar fusion, ensuring consciousness' survival long after the last natural star burns out. But not all worlds orbit stars. Some planets wander the cosmic darkness alone, carrying their own mysterious possibilities. Drifting through the darkness between stars are worlds without suns, ejected from their birth systems to wander the galaxy as cosmic orphans carrying hidden oceans beneath frozen shells. Rogue planets, also called free-floating planets, exist in interstellar space without orbiting any star. These wandering worlds were either ejected from their original solar systems during chaotic early formation periods, or formed independently in the dark clouds between stars. Astronomers estimate our galaxy contains billions, or even trillions of rogue planets, potentially outnumbering starbound worlds by factors of hundreds or thousands. Think of rogue planets as cosmic icebergs floating in an ocean of darkness. Without a star's warmth, their surfaces freeze to temperatures approaching absolute zero. Any atmosphere they once possessed would condense and fall as snow, creating landscapes of frozen nitrogen, oxygen, and carbon dioxide under skies black as the void. But beneath these frozen surfaces, some rogue planets might harbor conditions suitable for life. Planets with thick atmospheres or substantial radioactive decay in their cores could maintain liquid oceans beneath miles of ice. These hidden seas might remain warm for billions of years, powered by geothermal energy instead of starlight. Jupiter-sized rogue planets could generate enough internal heat through gravitational compression to keep vast oceans liquid for longer than the universe's current age. These wandering water worlds might support complex ecosystems based on chemosynthesis rather than photosynthesis, similar to life forms around Earth's deep-sea hydrothermal vents. Recent surveys suggest rogue planets might be surprisingly common. Some estimates indicate that for every star in the galaxy, there might be 2 or more free-floating planets wandering the interstellar medium. This would mean trillions of hidden worlds drifting unseen through the cosmic dark. For humanity's distant future, rogue planets represent both opportunities and challenges. They could provide resources and habitable environments for interstellar travelers, but they also remind us that most of the galaxy's real estate exists in cold darkness, far from any star's warming light. As we contemplate spreading beyond our solar system, we must prepare for a universe where most habitable worlds drift in eternal night, powered by the heat of their own formation and the slow decay of radioactive elements deep within their cores. But even the longest-lived stars and most stable rogue planets cannot escape the ultimate fate awaiting all energy in the universe. 13.8 billion years from now, when the last star flickers out and the final black hole evaporates, the universe will reach a state of maximum entropy where no more work can be done, and time itself becomes meaningless. The heat death of the universe represents the ultimate deadline for all conscious beings. According to thermodynamics laws, energy constantly flows from hot to cold, and this process cannot be reversed without adding more energy from somewhere else. Eventually, the universe will reach thermal equilibrium where no energy gradients exist to power stars, planets, or life. This cosmic endgame unfolds over timescales that dwarf human comprehension. In roughly 5 billion years, our sun will exhaust its hydrogen fuel and expand into a red giant, vaporizing Earth's oceans and atmosphere. But this represents just the opening notes of a destruction symphony that will play for trillions upon trillions of years. In 100 trillion years, star formation will cease as galaxies exhaust their gas supplies. The universe will enter what astronomers call the degenerate era, populated only by white dwarfs, neutron stars, and black holes slowly cooling in the expanding darkness. But even these stellar corpses won't last forever. Protons, the fundamental building blocks of ordinary matter, may decay with a half-life of roughly 10 to the 34th power years. If this prediction proves correct, all atoms will eventually disintegrate, leaving behind only electrons, positrons, neutrinos, and photons in an increasingly dilute cosmic soup. Black holes, the most long-lived objects in the universe, will persist long after proton decay, but even they cannot escape thermodynamics. Stephen Hawking discovered that black holes slowly evaporate by emitting radiation, with the largest holes taking roughly 10 to the 100th power years to completely disappear. The final era of the universe will be dominated by an increasingly thin gas of elementary particles and photons with temperatures approaching absolute zero. No complex structures can exist in this environment. Not chemistry, not biology, not consciousness. Just elementary particles drifting apart in an ever-expanding void. Yet some theoretical physicists propose ways intelligence might survive even this ultimate catastrophe. Advanced civilizations could potentially harness energy from proton decay or black hole evaporation to power incredibly efficient computers. These systems could run conscious minds at such slow speeds that subjective time extends indefinitely, even as the universe grows cold. For humanity's immediate future, heat death provides crucial perspective on our cosmic significance. We exist during a brief window when the universe contains enough organized energy to support complex structures like stars, planets, and life. Making the most of this opportunity might be our species' most important responsibility. The transition from planetary to cosmic civilization could be just the beginning of an even greater transformation. The choice facing humanity is simple, yet profound. Evolve into a cosmic civilization capable of surviving stellar death, or remain forever trapped on a single world awaiting extinction. Becoming a truly spacefaring species requires more than just building better rockets or developing faster propulsion systems. It demands a fundamental transformation of human consciousness, biology, and social organization. We must evolve from planetary creatures into beings capable of thriving in environments that would instantly kill any Earth-born organism. The transition will happen in stages, each representing a quantum leap in our capabilities and cosmic perspective. First comes mastery of our own solar system, establishing self-sustaining colonies on Mars, mining asteroids for resources, and building rotating habitats in space. This phase could begin within the next century if we maintain our current technological progress rate. The second phase involves reaching nearby star systems using whatever propulsion technology we can develop, whether through generation ships, fusion rockets, or exotic physics we haven't discovered yet. The first interstellar colonies will mark humanity's transition from a single-world species to a multi-system civilization. But The real transformation happens in the third phase, when human settlements become self-sustaining across multiple star systems. At this point, we achieve true cosmic redundancy. No single catastrophe can eliminate our species. We become immune to asteroid impacts, supervolcano eruptions, gamma-ray bursts, and even our home star's death. This distributed civilization would need to develop new forms of government, economics, and communication adapted to vast distances between worlds. A message sent from Earth to Proxima Centauri takes 4.25 years to arrive. Building consensus across interstellar distances requires patience and planning on scales no human society has ever achieved. Advanced spacefaring civilizations might barely resemble modern humans. Genetic engineering could adapt our bodies to different gravity levels, radiation environments, and atmospheric compositions. Cybernetic enhancements might allow direct interface with spacecraft systems. Digital consciousness could enable exploration of environments too dangerous for biological bodies. Perhaps most importantly, becoming spacefaring means accepting responsibility for preserving and spreading life throughout the universe. We might be the only conscious beings in our cosmic neighborhood, making us custodians of billions of years of evolution. Our expansion could determine whether intelligence survives and flourishes among the stars. The alternative is sobering. Every species remaining bound to a single world eventually faces extinction. Stars die, planets become uninhabitable, and cosmic catastrophes reset the evolutionary clock. Without spaceflight, consciousness itself might be nothing more than a brief flicker in an otherwise lifeless universe. But if we succeed in spreading beyond Earth, we could become something unprecedented in cosmic history, a species that outlives the stars themselves. Our descendants might witness the formation and destruction of galaxies, guide life's evolution throughout the cosmos, and possibly even survive the universe's heat death itself. The journey from planetary to cosmic civilization represents the next great chapter in human evolution. We stand at this transformation's threshold with the technology to begin serious interstellar exploration within our lifetimes. The question isn't whether we can leave our solar system. The question is whether we have the wisdom and determination to become worthy of the stars. The cosmos is waiting. The choice is ours.